Swayam Prabha. Digital India. Educated India.
Good morning. Welcome you all to this next lecture in this course on analytical, spectral and microscopy applications of inorganic compounds and nanomaterials. We have seen a plethora of spectroscopy techniques till now, maybe more than a dozen spectroscopy techniques. Of course, some analytical techniques as well. Let us look into one of the important extension of the spectroscopy, but it is a diffraction technique. So, this is a unique technique that comes under the diffraction method, and it is very highly useful for all the compounds, organic, inorganic as well. Of course, in the case of inorganic and nanomaterials, there is a huge amount of application is there. So, this topic is going to be on the applications of the powder XRD towards the inorganic systems. I am sure every one of us have studied even in the high school, like 11th and 12th, a lattice, a unit cell, a solid, a crystal, so all of these terms, and little beyond that itself studied. So, we will try to build using those concepts we already know into the how one can interpret the powder X-ray diffractions, leading to some informations on the structure, etc., or type of specimen you have, or the nature of the compound that you have, all those phase, all these kinds of things can be studied. So, for this, the first thing that we need to look at is that diffraction. We know very well the diffraction is nothing but when you have some object in the passage of the light bends and goes. So, this is the bending process of that, and that if you wanted to see a little more closer way, I am sure every one of us know what the grating is. Grating has got a very fine lines which you cannot see with the eye, because the lines are separated by a few micron kind of a things. Now, if you incident the light on this, obviously what you get is a diffraction, which means the light, it gets scattered in different wavelengths and separates out, and then you would look at that. Now, if you look at the lattice crystal, the crystal has got the lattices, and the lattice has got the atoms, and the atom has got the electron. Now, if you put the X radiation onto that, if you incident the X radiation onto such a crystal, having such a lattice, having such an atom, having such electron density, now that electron density is being reflected. Now, this can happen from every atom, every plane, and entire lattice. So, therefore, you have so many light, the waves, X radiation waves, which are scattered by each center. So, those light waves would in turn get overlaid either the constructive way or the destructive way. Okay. So, if you have a constructive way of overlap of these individual scattered X-ray beams, then this will result in a pattern that is present, and if they are destructively overlapped, then obviously you will not see anything. So, this is what basically is the X-ray diffraction. So, to have the X-ray diffraction, obviously you need a lattice, you need electron density, of course you can visualize the planes, etc., on that once you have a lattice, and then this overlap of these, the overlap is also called the interference in a constructive way, interference in destructive way. So, individuals atom, each atom acts like a scatterer. So, the scattering strength, how much is every atom is a scatter of equal strength? Absolutely no, because the scattering strength is dependent upon the electron density. So, therefore, you have one atom to other atom, electron density is absolutely different, therefore you have a different scattering strengths. Now the next point we have looked at is the overlap of all this, the overlap, the interference. So interference of the individual scattered beams. So these scattered beams can the overlay and give either a constructed beam or a destructive kind of thing. So this is the one which leads to the presence of an X-ray beam there, or not presence of a X-ray beam. So that is called a presence and an absence. That is what entire thing makes. So the lattice versus the presence and the absence of the X-ray diffraction spots has a great relevance relation, and this relation, which we will not go into detail, is called reciprocal relation. So if you look at the planes, the atoms in your crystal versus the spots which are found in the X-ray diffracted film, there is a inverse relation, or it's called reciprocal lattice relation. Just that I mentioned, but we don't need to go into the details. So I said that there is a diffraction, there is a scattering by each atom, and these waves constructively or destructively. So let us look at that part of it, and I draw your attention to the to this particular slide. You can see here is a line which is basically a plane, but now represented here in 2 dimensions as a line, and so another line, etc. So written as atomic plane but drawn as a line. So a plane in a 2 dimension looks like a line. So that is what. So you have, in fact, the plane is in the 2 dimensions, the line is in 1 dimension, and the lattice and the crystal is in all 3 dimensions. So to make the things easier, this is the concept which is being used. So you have one layer, you have another layer, you have another layer, like that. So you have one atomic plane, another atomic plane, another atomic plane, and each atomic plane has got atoms depending upon the type of lattice, etc., which we will look at later on. So when the X radiation falls, the scattering occurs from each of these atoms. So you can see, so this X radiation scattered by this and then going in this. So this radiation coming and incidenting on the atom or the plane in a angle which is called theta of that, and the reflected. So this is where the scattered beam, and there is another plane here, and which is scattered beam. So these beams can overlay constructively or destructively and result in a resultant wave, and if that is a constructive, you will see the spot, the corresponding the dark spot here in the film, and if it is destructively, nothing, gap. So a dark spot and no spot. That is what is called presence and absence. Presence of a reflection, absence of a reflection. So each of these spots in this particular film is called a reflection. So now you have a relation between this particular angle in which it is incidenting and the overlap between the 2 layers. So this is one and this is the other. So this particular wave travels extra by this particular vector and this particular vector, and then comes out. So the distance difference, the distance traveled by this particular X-ray wave between the atomic plane, let's call the top one as 1, atomic plane, that let's call this as a 2, and these two have this one. So if you take this particular distance as d between the 2 layers, and this is nothing but d sine theta, and this is again another 2 d sine theta. So therefore total extra travel that took place by this particular wave as compared to this particular wave is called wave 1, this is labeled as wave 2. The wave 1 has traveled by d sine theta plus d sine theta 2d sine theta as compared to the wave 2. Okay, so that must be the integral of the lambda. So therefore that is where you get these two together, the things here. So you have the X radiation impinging on this and coming out this another layer. So this is the distance extra, this is the d, so this is the theta, so therefore d sine theta, and then this slope will tell you this is extra, this is another d sine theta which is already shown over there, and this is the lambda of the wavelength should be n lambda to have a constructive interference lambda sine theta plus lambda sine theta. So that is what is called to d sine theta, d sine theta to d sine theta. So that is what the, so this is for the constructive interference. This gives a diffraction spot, and this is also known as reflection. So in this, so how this is labeled etc. will come in a minute. Now you got, so this is the basic criteria for the X-ray diffraction to be occurring, X-ray diffraction to be seen on a film or not seen. So present and absence. So when you have other conditions, not this particular condition, then there is no constructive interference, then therefore there is no spot on that. And this is what is the famous, which you must have studied in 11th standard itself, is the Bragg's law or Bragg's equation. Okay, so Lorentz-Bragg's equation. Okay, so that is what is basically written over here. And now if you look at this, this is the called X-ray photograph. Okay, in this X-ray photograph you can see the spots are arranged in certain order because you know your atoms in the lattice or orderly manner. And I told you the relation between the crystal lattice planes and diffraction spots. This particular thing is an inverse relation. So this is what is called the reciprocal lattice. This you can see in the form of X-ray diffraction. This you cannot see with your eyes, and using this you are trying to construct back this one, and that is what is called the X-ray crystallography solution. So you solve this particular spots which are having some internal relation and which is known as the reciprocal lattice, which is a reciprocal of the original lattice. So the original lattice will contain your compound, your molecule, its structure, everything. So therefore if you have this data can be collected from the X-ray diffraction, and this data will give you whatever the reciprocal lattice points are there. From these points order for their intensities, whether they are present, they are absent. Using this information you can bring back this one. Okay. So of course there are a lot of theory etc. are there which we will not go into the detail because this is just an application course. So we are restricted, but every unknown parameter will be defined. I will not take you through that. I hope this part of the X-ray diffraction is clear. So just like your light diffraction, X-ray diffraction, each atom has electron density will scatter the X radiation, and the scattered radiations will overlay constructively or destructively interfere and result in the diffraction spots, and which also called the reflections. And there is a pattern which is found in the diffraction spots. It is called the diffraction pattern. Also using such a pattern and using certain mathematical relations which will not be a part of this course, you can reveal what the lattice is. That is how you get the things. Okay. So for this I have been talking about the crystal, and then you have the lattice, and then you have the unit cell. So I am sure all these are studied even before the 12th standard itself. You know, in a lattice you have an infinite having huge number of atoms arranged in a particular order. If you keep connecting these atoms, you will find the smallest repetitive unit, and that is what is called the unit cell. This is smallest repetitive unit, and that is already understood. So that means by repeating that unit in 3 dimensions, you will build the lattice. So from lattice you have the unit cell, from the unit cell you have the lattice. Okay, and so that is, and where these unit cell axes intersect, okay, so that is what basically is the axis of this crystallographic axis. Can be Z, can be X, can be Y. These are referred as the crystallographic axis. So crystallographic axes are the ones which are emanating from the unit cell, where these axes will have a common intersection point. So that is what it is. Now again I draw your attention to this. So you can take this particular box is a smallest repetitive unit of a huge lattice that is present here, which is not shown over here, and therefore this box, many times people remember it as a box. It is a box because you have enclosed from all directions, but otherwise it's a unit cell having three-dimensional parameters. So here you can see the Z, and you can see the X, Y, and the X. So all these three. So those are called the crystallographic axis, and this particular cube-like structure or box-like structure is called the unit cell. Okay, so unit cell is the smallest, the identity unit, or which upon repeating in all the directions you will be able to build the lattice. That's where the thing is. Okay, now so this we have talked about in the previous concept explaining case for the Bravais lattice. We looked at the atoms presenting in a plane, etc., and the same thing we can try to understand from this particular concept of unit cell. Now, so this crystallographic axis, you have X, Y, and Z, and if you take any plane containing atoms, and look at this plane, how it is oriented with respect to X axis, with respect to Y axis, with respect to Z axis. So if you take this particular shaded one in this slide, what I am showing with this cursor is shown as a pinkish color, and is written as 1 0 kind of thing that you have. Okay, so this particular thing cuts the X axis at this value, and the reflection of this cuts at the Y, and it does not cut at all on the Z. Okay, so like that you have, so the plane parallel to one of the axes, and that means it does not cut, whereas it cuts the other two axes here. Similarly you can have the other one, so you can have one with the 1 0 0. So this means this particular plane will intersect with the X axis at 1. So you can see that this is your X axis, and this is 1 unit length, and whereas in the Y it does not, it is infinite, and Z it is also not intersecting, it is a infinite. So that is where thing is. So therefore 1 by intersection, 1 by 1, 1 by infinite, 1 by infinite. So this is along X, this is along Y, this is along Z. So these values, the inverse of this, 1 by 1 is 1, 1 by infinity is 0, 1 by infinity is 0, and this is what is called the Miller index. So these are Miller indices. So that means in a lattice you can visualize the planes of atoms, and these planes of atoms can be identified, notified with a convention called HKL, which is called the Miller index. Now if I tell the HKL, and if I know the lattice type or unit cell, then I know where exactly it is. Of course it is a family of things. If you multiply with n, so it will be 200, 300, 400, etc. They are all parallel planes. It's called family of planes, and this will have a intersection of a half, this will have cutting at 1/3, this will have 1/4, etc., but they are all family of planes. Okay, so that is what you call the Miller indices. So now you understand that. So you have the 1 0 0 which is cutting the X axis, 0 1 0 which is cutting the Y axis at unit length, and 0 0 1 which is cutting the Z axis at 1. Now, if it cuts all of them at 1 1 1, it is called the 1 1 plane, and it is not parallel to any of the x y z. Any of the x y z, you can see here it is cutting this particular triangular plane here, you see, cutting z axis at one length, y axis at one length, x axis at one length, 1 1 1. So, this is 1 1 1 by 1. So, this is. Now, here you have seen already, I explained to you Gen 1 infinity infinity and etc. Here this is at 1, y is half, z is equal to 1 by 3. So, this is at 1 half 1 by 3. So, it is the where it is cutting. So, inverse of this is 1 by 1 1, 1 by half 2, 1 by 1/3 is. So, this HKL is 1 2 3. So, you can see as 1 2 3. So, what is that we learned? We learned that we can look at the planes containing atoms, atoms containing electrons. Therefore, the planes will diffract. So, in general we use the word the plane diffracting. It is not actually the plane which is diffracting, it is the atoms which scatter, and the scattered radiation overlay, and then the diffraction comes in that. But in a thing. So, this is used as the HKL. Of course, for hexagonal you can use 4 axes, therefore the 4 number, but it is not important, you can just see that. So, this was basically proposed by the British mineralogist crystallographer William Hallowes Miller in very early days itself. It is basically called the crystallography, etc. So, these are the Miller indices. Let us look at to understand this a little bit better. On this slide, I once again draw your attention to this particular slide, which shows a number of planes and just a kind of a homework which I am doing in the class itself, and it becomes a kind of a tutorial for you. So, let us look at this Miller indices tutorial here. Okay. So, this particular plane, the bluish shaded plane which you are looking at, it is cutting the z axis at 1, does not cut the y, does not cut the x. So, therefore, that is 0 0 1. Okay. And here this cuts at the x and does not cut y, does not cut z, and this is 1 0 0 and analogously 0 1 0. Now, here 2 of them. So, this pinkish kind of a thing. So, it is cutting this particular axis called z at 1, this axis called x at 1, and not with the y. So, therefore, 1 0 1, because 1 by 1, 1 by infinity and 1 by 1. So, 1 0 1. Now, here you look at the other one. So, it is cutting this particular x at the 1 and the y at the 1, but not the z. So, it is a parallel to the z axis, but not to the other axis. So, 1 1 0. Now, you can see other one here, it basically intersects here at the z, intersects here at the y. So, at 1 and 1, but whereas x, it is parallel, does not intersect. So, 1 by infinity 0 0 1 1. Now, we have done so much of quite a much of exercise. Now, this I have already said in the previous slide, 1 1 1. You can also have on the negative side of the axis, that will become 1 bar, but the concept is the same, the other side, and you have, so those you can also have negative of these. So, this HKL need not be positive, it can be negative is shown as a bar L, or it can be HK bar L or HKL bar, or you can have H bar K bar L, H bar L K L bar. All the combinations are possible with 1 negative plane, 2 negative planes, 3 negative, all 3 negative indices negative. It's all possible. Now, that's, as I mentioned, that these are all called the family of things. So, you can see 1 0 0, 1 0 0, 1 bar 0, 0 1 0, all of these for 1 1 0 family and 1 1 1 family, and there. So, you can sit and work out all this. So, in the negative axis, if you have, the -1 will come into that. So, here you have the 1 at the x axis and 1 by 4 at the y axis and the infinity at the z axis, and that will give you 1 by 1, 1 by 1 by 4 and 1 by infinity. So, that is where 1 4 0. So, you can see all of them. So therefore this. So with this, I guess the tutorial of this you need to sit and work out, and these are already being done to you in the 12th standard and definitely in your BSc first second year. All these are, it's just a refreshing for you, because this has some relevance with the powder pattern and some relevance with the structure. That's why I'm introducing that without leaving it to you just completely read, but you need to read basically in that. Okay, so we looked at the imaginary planes with the adding lattice. Here we showed some crystal structures, the sodium chloride. So you can see the sodium atom and the chloride atom. The chloride atom is the bigger ball because anions are much bigger, cations are smaller. So therefore this lattice, and if you try to make a plane here, a plane here, a plane here, so you can see this plane is coming from the 2 0 0, and here these planes are with respect to this, with respect to this. So here this one is a plane, but here you are looking at this as a plane and this as another plane. So see that. So this is 2 2 0 kind of thing, and this is 1 1 0 kind of thing. So all these planes and the interplanar distances, the plane distance of the plane from the origin, which you can call it as a DHKL, and you can also find the plane. That means the DHKL is the distance between the parallel planes of the HKL. That is the distance, and this distance is with respect to the common crystallographic crossing of the axis. With respect to that, you can see that D110, this is being found. This has a lot implication again in this particular diffraction course, even if it is application. So we started with the lattice, we went into the unit cell, we went into the crystallographic axis, they cross that one, and the axis which offer the crystal lattice or unit cell, then atomic planes, then we come to the Miller indices, then we looked at the interplanar distances. In a while later I will give you these distances, how the values, you don't need to sit and work out, all of them are very well known. So what we have looked at is the basic aspects, and now if you look at the powder X-ray diffraction, powder X-ray diffraction is one of the very important analytical techniques among all. It's a diffraction technique, I already explained to you, using which you can study the structure of the material, phase, crystalline phase of the material, and many traits, many properties of such a material can be. You can study the unit cell dimensions, you can study the whole structure itself of the things, three-dimensional structure. Of course, it is easy to get from the single crystal XRD. From powder XRD, you can get the lattice parameters, you can reasonably get even the structure if some basic structures are known, similar kind of structures are known for materials having the same kind of a structural unit or same kind of a lattice, etc. So basically what they do is they take the compound, make into powder, and then use that as the bulk material. So when you shine the X radiation on the crystal, of course as I talk to you, it will diffract, and the diffraction pattern present, absent, absent, present, absent. Where there is a X radiation has come, it will give a spot on the film, and when there is no radiation, there is no spot. So that is how you see, that's what is called the pattern coming in. So based on the diffraction pattern, this is very unique to that particular lattice, not to the type of the lattice but also the type of the atoms present. Why? We already studied in the beginning of this particular lecture that the strength of the diffraction does dependent upon the number of electrons present in that particular scatterer, which is called atom. Okay, so therefore, so if you have somewhere some atom and another different atom, obviously if their number of electrons are more, this scattering strength, that means your intensity pattern. So therefore you have a very unique kind of a the X-ray diffraction patterns. Therefore you can easily find out the what phase, crystalline phase. You can also find your major phase, your small impurity in that. So impurities will give its own lattice, and the major compound gives its own diffraction pattern. Then you can see the overlay of these, so therefore you can find out. and if they are separated out, you can find the percent of the such things also. So you can use for qualitative, you can also use for the quantitative kind of thing, and you can define, you can derive the lattice parameters, you can derive the crystal structure as a whole. If you have some other structures of similar lattice are known, and then you can use the refinement methods which are known, least square method, for getting the better position, thermal parameters, of course lattice constants, all of these. Okay. So from the powder XRD data, this getting the for complicated structures is not easy to get that, but for single crystal you can get all of them. But powdered X-ray diffraction, you don't need to get this full structure, but you can use whether this matches with something known, whether it does not match with something known. So that way you can identify many things, whatever is required. Show in a while. So the particle size can be basically derived from the peak width, peak pattern, etc., using the Scherrer formula. So this is the wavelength, this is the peak width, this is when you have a standard crystalline one, and the angle of diffraction. So using these things you can always make in this. Okay, we will come to more details of this, how we can use the long ways of the powder pattern into the structure, into the phase of the crystal, into the information, the purity, all of those things. As we keep going across, we will translate those parameters while. So we will look at those aspects in the coming up class. Thank you very much.